Today we're going to be talking about rates of change. So, average versus instantaneous rate of change. Remember, the average rate of change over an interval, I'm going to say from a to b, of some function f of x is f of b minus f of a all over b minus a. So it's the slope of a line through 2 points versus the instantaneous rate of change is the derivative f prime of x. And what this lesson has to do with is particle motion. So we're going to be talking about particles moving along a number line, essentially, and going back and forth. So think about driving your car. So the function s typically stands for position. So s of t typically stands for position of an object over a certain time period t. And so we're given delta s is s of t plus delta t minus s of t. Then we have a familiar formula. We know rate is distance over time. We know distance is rate times time. So if we're solving for the rate, that's going to be distance over time. The average velocity is change in distance. So s of b minus s of a all over b minus a. So that's our average velocity expression. Versus the instantaneous, we know that that is the derivative of our function. Okay, so again, if f sub t stands for our position function, the derivative of s of t is our velocity function. Okay, and typically velocity, remember, if we're going to talk about units, is some distance over some time. The absolute value of velocity is speed. Think of your speedometer. That's what the absolute value of velocity is. And then v prime of t is acceleration. And don't make fun of me, I can't spell the word acceleration. So v prime of t is acceleration. And so if you have a positive velocity, because velocity, remember, gives you a direction and it gives you how fast you're going. So velocity gives you a direction. I can't spell the word direction. And then how fast I'm going, which again is a fancy way of saying speed. So if you have a positive velocity, you are moving left or right if you're on like a number line, like an x-axis, like the x-axis, or up if you're like on a y-axis. Negative velocity, you're moving left or down in relation to your starting point. Okay, so let's do a few examples. A tennis ball is dropped from a height of 150 feet. The ball's height s at time t is given by that position function, where s is measured in feet and t is measured in seconds. So in the book, just so you guys know, they're going to give you a general formula that if you're in physics, you should recognize. And the AP always gives you what your, I don't know what that was, always gives you what your position function is. Okay? So don't worry. They're always going to give you, they're not going to make you build the formula like we do in physics. Okay, So anyway, average velocity over an interval is given by s of 2 minus s of 1 all over 2 minus 1. So that is 86 minus 134 all over 1. So a negative 48 feet per second. Versus the instantaneous velocity, well, that is the derivative of s of t, which is negative 32t. And so I want this I'm going to change this. You'll see why in a minute. I'm going to change it to 1.2. I apologize. So I now need to find s prime of t, which equals v of t. And I'm not thinking today. I apologize. I'm finding s prime of 1.2, which again equals v of 1.2. So I plug in 1.2, and that gets me negative 38.4 feet per second. Indicate units of measure means give me my units. Okay, and then now, is there a time on the interval where my average velocity, which was this negative 48, equals the instantaneous velocity? Well, the expression for instantaneous velocity is that when I divide, I get 1.5 seconds. That's why I had to change part B, just so you know. Okay, example 2. A diver jumps from a platform diving board that is 32 feet above the water. The initial velocity of our diver is 16 feet per second. The diver's position at any time t is given by this formula. So again, the book is going to have you get this formula. They give you the general formula that, again, if you're in physics, it should look familiar. They're going to give you the general formula, and you're going to have to plug in this initial velocity, which, just so you know, is v sub 0. The initial position is s sub 0. Okay, but I give you the function. I'm just going to give you the functions because we're not in physics. We're in calculus. I want you to do the calculus, not the physics. Anyway, when does the driver hit the water? So I set my equation equal to 0. And I factor out a negative 16 because that is a common factor of everything. I factor that out right? Yes, I factored that out right. Okay, I apologize. My notes have this incorrect, so that's why I'm a little confused. Okay, so t minus 2 times by t plus 1 just double checking that's right. Okay, so set each one of those factors equal to 0. So I get 2 and negative 1. We do not have a DeLorean. We do not have a time machine. So we ignore that one. And we deal with s of 2. So what is the diver's velocity and impact? Okay, so my velocity is the derivative of position, so that's negative 32. Negative 32t plus 16. So I find s prime of 2. I am not focused today. I apologize. Which is negative 32 times 2 plus 16. So I have a negative 64 plus 16. So negative 48. And let's give me some units. My units are feet per second. Okay, example 3. Particle moves along a line so its position is given by this function. Quite honestly, this is more typical of what you're going to see, more typical of what I'm going to give you. I'm going to give you a position function. And then we're going to have to find a bunch of stuff with this, okay? So find the equations for the velocity and acceleration. So my velocity is the derivative of position, which is that function. I forgot to take the derivative of the next term. Okay, and then my acceleration function is the derivative of velocity, which is 6t minus 18. So find when the particle is moving left and right. So first I have to find when v of t equals 0. There's a common factor of 3 that I'm going to factor out. And I'm going to factor it out correctly this time. So I solve this equation, and I'm going to factor this correctly. So a minus 4, t minus 2. So you figure out when your velocity equals 0. Okay, now you do a little number line chart to determine, okay, this is a number line, so this is my velocity, and we started 0. So on the interval from 0 to 2, plug in a number from 0 to 2. So if I were to plug in 1, what is your velocity? Is your velocity positive or negative? If I plug in 1, my velocity is positive. If I plug in something between 2 and 4, say 3, I am negative. And then between 4 or something greater than 4, I end up being positive again. So that tells me the sign of my velocity function. So if you go back, my velocity, I am moving right when I have a positive velocity, moving left when I have a negative velocity. So we are moving right when v of t is greater than 0, and that is from 0 to 2 and from 4 to infinity. I'm moving left when v of t is less than 0, and that's from 2 to 4. What is the particle's velocity when the acceleration is 0? Okay, so I set my acceleration function equal to 0 because I need to find that time. So I have now the time when my velocity equals 0. I now need to, the acceleration is 0. I need to now find v of 3. Well, v of 3, I'm going to use this formula here because I just think it's going to be easier. The reason I know it's going to be easier because when I subtract 3 and 4, that's going to be a lot easier than me squaring 3, multiplying it to the 6. I just think it's easier. Okay, so our velocity when our acceleration is 0 is negative 3. So I want you to notice on this interval, 3 is on that interval. I'm negative on that interval. 3 at time 3, our velocity ended up being negative. Okay, so that's my video on rates of change. So basically, particle motion.